Turn on your camera. And share your screen. Perfect. And then you can see it right here. And you'll just have to click through your computer to change the slides. And then you'll be able to talk.
Okay.
Okay, so we'll start with our first speaker, Jan Stoica. I don't know, Jan probably doesn't need an introduction. He's a star in computer systems, networking. He has done amazing work in those areas. He's a professor at UC Berkeley. So Jan started multiple industries like companies, Conviva Network, Databricks, Anyscale, and it seems like whatever Jan touches turns out to be gold. And he has won many awards. He's an SCM fellow. And if you look at like early career awards, Sloan fellow, PICAS awards, and so on. So we're really happy, Jan, you are here today with us. Thank you.
Thank you so much. And very glad to be here. You hear me well? Perfect. So today I'm going to talk about some work I've done, with my colleagues and students over a couple of years, and just provides a context, over the past, 15 years, I've been lucky to be part of a few projects, and some of them, were reasonably successful as open source, some of them less so, but I've been working at different levels of layer of the stack, all the way from infrastructure and orchestration, distributed frameworks to make it easy to build distributed systems and applications, optimizations, engines for machine learning, and even a few applications on top. So during this talk, I'm going to present 3 projects, Ray, VLLM, and Chatbot Arena, at different layers of the stack. And actually, one builds on top of another. So Chatbot Arena is using VLLM is using Ray for in a distributed setting. Okay, so they are connected. They are not. So let me start with Ray. And Ray, we started the project in 2016. So what is the motivation behind Ray? Well, the motivation, even at that time, and you've seen this plot in some shape or form many times before, and this shows the amount of compute required to train state-of-the-art models. And that's a log scale plot. So basically a line means exponential growth. But fundamentally it's going, this plot is saying, if you believe it, is saying that the amount of compute required to train state-of-the-art models grows 10 times, 1 order of magnitude every 18 months. Okay. And why 18 months? Because 18 months was made famous by the Moore's law. During the heyday of the Moore's law, the compute capabilities of a single core was growing 2x, doubles every 18 months, so the same interval. Of course, as we know, the Moore's law kind of slowed down after 2000s, and now core performance grows only a few percent every 18 months. Okay, so now, of course, people, in order to bridge a gap, because it's a big gap because of Moore's law, and even more so from a single core, they developed, you have a lot of accelerators, right? GPUs, TPUs, and so forth. And the GPUs, and these are a few of them. And the GPUs and TPUs actually are successful in maintaining this kind of slope of doubling every 18 months the performance or things like that, like flops. And the reason they do that, because they do it, as you know, through innovation and further optimizations of the compute, right? Come up with tensor engines and things like that, different precisions, and still, they're able to grow much, faster to maintain fundament, basically more or less a Moore's law. But of course, the delta is still big because you are talking about doubling, every 18 months to growing 10 times every 18 months. And I don't have the data here, but this is another anecdote. OpenAI released every 2 years one of these models, starting from GPT-2, GPT-3, GPT-4, and soon GPT whatever, 5 or whatever they are going to call it. And in terms of the money, the GPT-2 cost $40K to train it. GPT-3 cost between 4.7 millions, whatever who you believe. So from 4 millions to 40 to 44 millions is the 10x. Then GPT-3 cost 100 millions to train. So it's another factor of 20, 25x. And it's rumored that the next model, which is trained by OpenAI, is going to cost between 1 and 3 billions. Okay, so it's another 20x increase. Again, so you compose in 20x increase with the performance of the chip increased, and you are going to have even now like a 40x increase in the demand 2 years. Okay, so it's probably even more aggressive than this plot. Okay, but what does this mean? So this means fundamentally that it's in order to support these workloads, there is no way but to distribute them. And you are not only going to distribute on a homogeneous machine, but it's going to be a heterogeneous machine, because now you are going to have to deal not only with CPUs, but also with GPUs, and not only with GPUs from NVIDIA, but TPUs and other accelerators from other companies. Okay, so that's a problem, right? Now, this is, again, to go further, it's not only that. So basically, this means that the infrastructure complexity has grown dramatically. At the same time, the workload complexity has grown, right? This is a very simple recommendation system, and what do? You get the data, you get the logs from the users, you pre-process them, you compute, do featureization, the old days, now you do embeddings, compute the embeddings, then you do some training or pre-training, then you do tuning and fine-tuning, then you do serving, right? You serve these models, right? And you get more data, and then you train more. And also, when you train, you do evaluations, so each batch prediction, right? Before you release a new model in production, you have to test it on the existing data, old data, so you do this batch prediction, right? So this is what you need to do. And each of these stages has to be distributed. And you do have systems, and we build systems over the years to distribute each of these stage. The point is that when you want to put them together and to build the entire pipeline or build your machine learning platform, the problem is that needs to stitch them together. And there are a few issues with that, right? One is hard to develop because each of these systems has a different API, makes it more difficult to develop. The other one is hard to deploy and hard to manage because you have to deal with these different distributed systems, which have also different, for instance, semantics for failures, recovery from failures, and things like that. And even it's also slow because between different systems, you need to when you move the data, you typically move through a blob store. You save on S3, you read from S3, you need to serialize, deserialize, and so forth. So that's also kind of slow. Okay, so that's kind of what the problem Ray tries to solve, is how to make it easier to support this complex application or a very complex infrastructure. And the way doing it is providing a very general distributed framework layer on which, and then because it's kind of quite general, unlike the frameworks before it, or most of them before it, is that you can, all these different stages, you can support on the same system, right? So unify these workloads, okay? That's basically the TLDR. This is what we built Ray in the first place. So now this becomes libraries on top of Ray instead of being different systems, okay? Now, the Ray is part, it's Ray core, the bottom one, and then there are a bunch of libraries on top of it for different workloads. The core, or the Ray core, has a very minimalist API, okay? This is basically the core API, and I'm going to give examples about how they are used, some of these APIs. But let me try to, argue why Ray is general, right? And we call this kind of, for a lack of better term, fast compute model. So first of all, it supports both stateless and stateful operators, right? So it has tasks which are remote functions. Think about RPC. RPC is a very basic concept, which you can do almost everything with RPC. In addition, has actors, which are stateful operators. And the other way to think about it is that you take the main compute abstractions you have in almost any language, at least, and like most of the languages. So you have functions and classes, right? And then this allows you, task and actors is basically transparently and remotely run instantiating and running functions remotely, right? This is tasks. And classes you can instantiate remotely. These are actors. They have some state, right? In addition, you have this concept of future. So the future enable basically parallelism, like you'll see. Basically, you call a function, which is remote, and it returns immediately with a pointer, with a reference to the result. So you don't need to wait to launch another function, like you'll see. And finally, it's shared in memory distributed object store. So the things to think about, the way to think about that, it allows you to pass the values equivalent by reference. You have two ways to pass the values when you invoke a function. You learn that is by value, right, as an argument of the function, or by reference. You provide the reference to the data, and this is typically used when you have large amounts of data. Okay, that's basically, this is what Ray is. Okay, let me show you how, it's the core, the backend is built in C, C++ for performance reasons. And you have bindings for different languages. By far, the most mature is for Python. So I'm going to show a few examples with Python. So here's a very simple, trivial example. You have a function f. It takes 1 second, and you call that twice. Of course, if you are running on your machines, the entire program is going to take 2 seconds, right? Now, how this is going to work in Ray? First of all, you use these decorators, Ray remote, to indicate that this function can be run remotely by the system. And you call f.remote A and f.remote B instead of just f of A and f of B. Okay? And then you get the results because, like you'll see, this f.remote are going to provide a reference, not the actual value. Okay, so when you run every remote A, you are going to immediately issue a task of the function to run remotely, and you are going to get immediately back a reference to the result, right? At this point, this function f, although this figure doesn't accurately shows, it was just submitted. Maybe it wasn't even scheduled or sent to a particular node, right? And the point now, because you get the reference, you can immediately execute the next call, which is f.remote B, and say you are going to instantiate on a different worker, right? And again, you get the reference back. And now this is asynchronous calls, non-blocking call, like I mentioned. And now you want to get the results, you do ray.get on the references of the futures of f of A and f of B. And now it's blocking and you wait for the results to come back. Now, the point here is that during this time, this f of A and f of B can run in parallel, right? So if there is no data dependency, all of them can run in parallel, assuming you have enough cores, right? And now the entire program is 1 second, right? That's basically what it is. Very simple. Like I mentioned, classes also support classes. When you instantiate them remotely, you are going to have this kind of actors, right? It's kind of some entity which runs out there and waits for methods to get method to execute, and you can invoke these methods. Okay, so that's pretty much it. From day one, the one thing we've done, and I think was a good decision, is also to provide some support for accelerators. And so basically here we allow the developers to specify what are the requirements for their task or actors. So you can say, for instance, I want 2 CPUs and 1 GPU. You can also support fractional GPUs and things like that. Now, you can ask yourself, why don't you, Ray, figure out this, what needs resources? Well, it's hard. So first of all, you try to provide, to enable the developer to provide this kind of information like hints. In the future, if you can do that automatically, you can ignore the hints. Okay, so that's basically what it is. So these are the two concepts, task and actors. Now in shared memory, object store, and like let's consider this example. So you have a function G which calls a function F, right? So F returns a future, a IDX, and which is passed to G. So say when you return, and this is a distributed object store. So basically when you call this f.remote, like we saw before, you are going to get back a future. This is IDX. And this is, and when you call the second one, v.remote with a reference, then you are going, so this is what is going to happen. So remember, so the G depends on the reference which is returned by F, so it has to get the value which eventually is computed by F. So now what happens when F is done, right, is going to write the value, the result in the shared store, right? And then when it's available, then node 3 is going to, G, which runs on node 3 in this case, is going to be unblocked because now the dependency was resolved of the input, and is going to copy in the local object store X, and is going to take X and is going to execute. Okay? But the main point here, you see that this object X is transferred only between node 2 and node 3. Now, to give you the point about what is the advantage here, assume that you have single, like RPC. So what you have with RPC, which doesn't, don't send the reference, you send the values. So when you call X, when you call F, then you need to wait for the value to return. So X will be retransferred from node 2 to node 1, and then you are going to pass X to G, right? And then again, you transfer now X from node 1 to node 3, right? So because you don't have the ability to pass the data by reference, now you transfer X twice. Node 1 doesn't know X, doesn't need X, right? But just to pass it to G. Right. But this, you knew that, right? Because this is what you use even for a single machine when you pass, arguments by reference, because we want to avoid copies, right? So this is again Ray ecosystem, like I mentioned, have future, task, actors, and the object store. And right now there are a bunch of libraries for different workloads, for data processing, training, tuning, and serving, and reinforcement learning. Okay. So Ray has grown in popularity quite a bit, and more people and companies are using it for building their machine learning and AI pipeline and infrastructures. Okay, many of them. And here are a few examples. Ant Group I put here. This is the first big users, very early days. So they build their entire kind of AI stack on top of Ray. So you see Ray as a base, and with some support for some basic workloads. And then on top of that, they build a bunch of algorithms and modules. And then on top of that, services, and on top of that, applications, advertisement, recommendation, and things like that. And even now, like Ray is like more than 1/3 of their machines in the backend, they are running Ray. Okay, and the reason they do that is for the, I mentioned, right? It's because of unification. So we build, because you have only one framework to support all these applications. Right. Uber, if you remember, it was a pioneer for machine learning platform with Michelangelo. All these machine learning platforms, the first generation, they were built by stitching together the different systems for data processing, featureization, training, serving, like Horovod for training and so forth. When they built the second version of their machine learning platforms, they pick Ray. And this happens with many other companies which build their second instantiation of machine learning platforms. This is Shopify, something similar. Now, and OpenAI trains their models on top of Ray, Cohere, and other foundation labs using Ray as some in one form, and except Google. So now, next, I'm going to say a little bit more. So this is what kind of Ray, and we call it classic Ray. But this year we started to look and back and look. Of course, we knew some of these limitations, and we decided to take action and resolve some of the limitations. Now, while Ray Core has some support for accelerators, because it allows a developer to say that I want to run this task on these GPUs or on this, and they can even say the type, like NVIDIA or AMD or whatever. That's kind of more on control plane. It doesn't have a lot of support, and I'll show you on the data plane. And the truth is that one of the major trends of our days is that you see a rapid transition from the CPU-centric to accelerator-centric world, right? Just to give you a sense, I've seen that, experience. In 2009, we started to build Spark. It was Hadoop days. It's very homogeneous system. You have a bunch of machines. Each machine has a CPU and some disk, right? The big transition from this to, SSDs, right? That's what's the big transition. Then when we started to build Ray, we have to start to worry about GPUs. It's actually this one of the limitation of Spark, because it was built on top of JVM, didn't support well GPUs, right? This is one. The other one, it was Spark was much more, BSP model. It was much more regular model, while for some AI application, we need, much generic compute models. But, you need to worry about NVIDIA, right? But today you have Azure, right? You have, and I should have put also ARM, because now it's popular as a CPU, but obviously you need to be worried about TPUs. NVIDIA, AMD is pretty good, AWS Trainium 2 is going to announce very soon, is going to be very performant and things like that, right? So you cannot ignore them. And Ray is very dynamic, very flexible, but you pay for that. It's like Python. It's very dynamic, can do anything, but it's very slow. So that's kind of, you need to pay the cost of RPC, dynamic memory allocation, difficulty to efficiently support peer-to-peer protocols like through RDMA, Nickel. So most of this on the data plane as well. So actually it's even worse, because for doing that, it requires upfront allocation of resources, because otherwise, if you don't do that, you can cause deadlock, right? I need to sync sender with receiver, and I allocate for sender, but I cannot have resources for the receiver, so kind of is deadlock, right? So let me give you a little bit of sense of what are kind of the issues, right? So this is the default execution of RAID core, and this is very simple things. You do echo, right? It's like you implement echo function. So basically, you send something and get back the same thing, and you call it in a chain, right? So basically, you call A, echo, and then A will call B, right? And then you want to return. So this is what happens. If you look at actually, if you do RPC, this is what will happen. You send hello, right? And you get back hello. And then you are going to send to B hello and get back. This is basically more or less what happened. Now, it turns out that, one thing I didn't say, Ray has multiple optimizations. So typically it gives you back the reference. But in some cases, when the reference is, when the value is very small, it can return you back the value. It's an optimization. But for you to know, is like when the data is small, if you, this is the way it's going to work, and this is how RPC is going to work. Right? So what you have here, the driver is going to be a bottleneck, because you have 4 copies of hellos you need to deal with, and 4 RPC. Now, this is how I've shown you Ray is going to behave, and this is when data are stored in the object store, right? So the driver, you have to call is hello is the argument. You are going to put hello in the object store, and then you are going to call A with the reference to hello. A is going to read hello from the object store. Then is going to his return. It's also hello. Is going to put in the object store. And it's going to send the reference to the second hello to the driver. The driver is going to use this reference to invoke B, and B is going to read hello and is going to write its output, which is again another version of hello, and then is going to get the reference from B to the driver, and the driver finally will read hello, right? So now, as you can see, now driver has only 2 data copies, right? Write hellos, get hellos from the B. The problem is that you have now 6 RPCs total you need to deal, right? So the new things we are adding a new API we call accelerated, dynamic acyclic graphs. So basically you declare the computation graph upfront, right? So it's a little bit more static but because it's static, you can optimize it. And the goal is to, run the task even if it's 1 millisecond, it's 1% overhead. And the GPU to GPU transfer is only 10 microseconds system overhead. So ideally, you want, when you use Ray, to be able to write programs have the same performance as you run on the bare hardware. Okay, so this is giving you how it's going to work. You basically you have this 2 actors like echo actor and echo actor, like before, but now you are going to create a DAG, right? You have DAG, your input node, and then you connect an input node with the next node using bind. So here you connect A and B, right? It's like, and so this is what you create a graph, right? By adding edges between different, this A and B are actors in this case. Okay, and now you call experimental compile, basically compile the DAG, and what happens when you compile is basically it's going to, for instance, it's going to allocate buffers, everywhere where it's needed. So static buffer allocation, and also it's going to start this A and B as an actors. And this is supposed to run, if you run the same thing, use the same graph to run for different inputs, then you don't need to pay the cost of creating new actors. You don't need to pay the cost of creating memory and things like that. And you don't need, you are going to get rid of quite a bit of RPC, right? So basically, this is what happens when you invoke execute on hello, this tag, this is what will happen, right? The driver will still write hello in the shared memory, but then A is going to get directly hello from the shared memory. There is no control message needed. And is going to write his result in the shared memory, which will be read by B, and we should write its own result. Okay, everything is pre-allocated. So now, and then the result is returned to the driver. So fundamentally, here you have an optimal number of messages. Okay, that's what it is. And even more, you have here, this is about how you communicate between 2 GPUs. And actually, you can have a way, because one thing, what you don't want to do it, and what happens today when you communicate between 2 GPUs, this is what happens today. Because the shared memory is across the RAM. It's not about GPU GRAM. So what you have when you communicate, you need to write between, for instance, from the sender to the receiver. The tensor is going to be written from the GPU RAM to the CPU RAM. Then it's going to transfer this from the CPU RAM, from the sender through the shared store to the GPU RAM, and from the receiver RAM. And so the receiver RAM is going to be transferred to the GPU RAM. It clearly is not very effective. However, what you can do is like with accelerated DAGs, you see there, I think it's here. You You can provide the hints, and you can provide also the hints about the control, the protocol, the protocol to use, in this case, nickel. And as a result, you can have direct communication between GPUs, right? Which of course can improve the performance dramatically. So this is a little bit about Ray. So the things to think about, to remember about Ray, it's a very general framework. It's basically support for both actors and stateless tasks, uses futures to provide, to give you, to enable parallelism, and a shared memory to allow you to pass the data by reference. And in addition, we have now working on this new construct, which is accelerated DAX, to declare statically the DAX whenever we have the opportunity to do so, because many of the computations and workloads in machine learning are repetitive, like if you think about the training, to eliminate most of the overhead and allow GPU to GPU communication and things like that. Yes?
Does Ray allow each node to have its own data, which is run to only run operations on its own data?
If it allows its own.
Does Ray support each node also having its own data?
Yes, totally. Yeah, it's fundamentally, it's again, like actually the shared object store, it's under the hood. You cannot, you can put a data in, you can have a put and get from the object store, but at the same time, it's Python code. You can do whatever. You can have local data, and you can read the data, and only if you want to pass to other actors or function, you can use a shared memory. Otherwise, you can use, and you can use anything else outside, right? You can establish your own communication. It doesn't stop you, right? Sorry, I don't know.
Can you specify which worker or which node you want to?
Yeah, the question, the question is whether you can specify where to place different computation and things like that. Great question. You can absolutely do it. So one way is basically to say that obviously you can define by requirements, and that you get a node which has these resources you need. But you can go to the next level and basically say, I want to run on this node. The way you do that, you can assign to each node what you call this kind of virtual resources. You can think about like labels, almost like in Kubernetes. And basically you can say, oh, I want, it's like virtual resources. You can declare whatever resource you want, and you associate with a node. That's the node one resource. And then when I run a task, I can say, oh, I want this resource, which is node one. And that will result in that task being scheduled on that node. So you have that. So the philosophy behind Ray is provides you all the flexibility you need. Of course, it's not going to be easy, because you need to, when you write programs, you need to be aware about parallelism. And as we know, writing parallel programs is not easy. So it's not a panacea, right? It's like, it allows you and makes a lot of things easier, but it does expose the parallelism, right? Which is unlike Spark, which doesn't expose the parallelism, but the price is that it's very good for a particular workload, which is parallel data processing, right? But if you want something more complicated, it's hard to do. Okay, VLLM. Okay, this will be shorter, I promise. So this VLLM, it's a serving engine, right? And when we started it, is of course you have this large language model you want to serve, and actually this started, like a little bit over 1 year ago, March last year, 1 year and a half maybe. And the point is that it's these large language models are very expensive to serve, right? Which even with a modest size, like 13B on A100, at that time, this was one of the top GPUs, you just get a few requests per second, right? And these are very expensive GPUs, right? So why is that? I know, I think everyone knows by now, but just to brief recap, because these LLMs generate tokens sequentially, right? One token at a time. You get the prompt, artificial intelligence is, and then based on this first tokens, you have the attention mechanisms, which kind of weight about the importance of each of these words, and they come with the most likely word based on the training corpus, based on the corpus they are trained, and in this case is right? And now you have this this kind of prefix, and based on the prefix, you come up with a new word and so forth, right? So it's linear, right? You have a part which is you are going to, you get the prompt, and when you get the prompt, you can do this attention in parallel, but then after that, you have to one token at a time, right? That's what it is. This is what. So you do not use the parallels of the GPU. So the GPU are basically idle, right? So what do? We know what you do, right? We are computer scientists. Well, if a request doesn't have enough parallelism, then process more requests at the same time, right? And this is a concept of batch. You put more requests in a batch and to process them concurrently. Now, what is the problem? You run out of memory, right? Why you run out of memory? Because, let's see, because remember, to compute the next token for a request, you need all the prefix. So now you have more requests to process in parallel. You need to keep more prefixes in memory. Now, the memory is organized this way, roughly speaking. This is 40 gigabytes memory for A100, again, more than 1 year ago. It was. So you have parameters of the weights. You have 13 billion parameters. Each parameter at that time, 16 bits, 2 bytes. So it's 226 gigabytes. Then you have some activation, which is in others, and you have the KV cache, which is basically contain the metadata associated, called embedding, associated with each of these tokens in the prefix, which are required to compute the next token, right? And this KV cache, for each of these tokens, it's a lot of data. An embedding is like 1 megabyte, right? So that's what it is. Now, the memory management in previous systems, it was contiguous. You pre-allocate. And there are good reasons to do that. Of course, one is simplicity. But obviously, the problem, you get a lot of wastage. And there are a lot of, and here I'm going to details a little bit what is the wastage. So first of all, you are going to have to guess how long is the output, right? So you need to allocate that, okay? And then you have to, you start to fill it in. Now, this is basically internal fragmentation. So you need to, so now, the one, and we make differentiation between, different kind of fragmentations. But one point I want to make, again, I want to go a little bit faster and want to emphasize what is important. Even if you know how long is the output, so the output is 148 bits, tokens. So I'm going to allocate 148 tokens. It's still not optimal because you are going to fill this 148, embeddings, one by one, right? So while I am filling, a big part of that, what I allocated, is unused, right? So just, so again, even if you know the output length, you haven't solved the problem yet, right? And then you have also this kind of external fragmentation, because if you look about, you can say for different outputs, even if you allocate, you are going to allocate different outputs lengths, right? There are types, and actually early on, when you go to OpenAI, you have to pay for different lengths, 8K or 2K or 4K. Now, once you allow to allocate to different lengths, you have also this kind of external fragmentation, in the sense of, imagine that you have only gaps of 2 kilo tokens, right? 2K tokens, right? And now you want to have something to allocate 4 tokens. You can have, 10 gaps of 2,000 tokens each, but you need to compact them. It's very complicated. So you don't, that's as you know. Okay, and this is pretty serious problem. And even if this is Oracle, this is Oracle, the green one, again, just look at the green one. The green one is what is the percentage of the KV cache it's used, right? The maximum is 38%, and that assumes that you know the length of the output. So how do you solve this problem? We know how to solve this problem. How do you solve this problem in systems? It's virtual memory, right? This is what kind of you do. This is how you kind of try to minimize internal fragmentation, get rid of the external fragmentation by having pages which have the same length, right? So this is basically what you do, right? So we have these embeddings, remembers, for each token. We have blocks of fixed size of a certain number of embeddings, and we allocate in the physical memory as the level of the blocks, and we have equivalent to the page table to go from the logical virtual address space to the physical address space. So here is an example, right? So from the point of view of the system, of the software, you still see the virtual address space, which is linear, right? Alan Turing is a computer scientist, right? And you have, in this case, each block has 4 tokens, embeddings. And obviously, in the physical memory, you can allocate the blocks wherever you have room for them. And then you have a block table like a page table, right? There are things which are easier in this case because here you add one at a time. You know, it's not like kind of random writes and things like that, right? It's one token at a time. So you just add to it. So for instance, you have a second field which says how many tokens you already have in that block. And now you are going to know where to write the next one, right? So now it's 2, you know, this, write it here. So this is the number of tokens in the second, in block 1 now is 3. And then when you finish with this block, you allocate another one, right? That's what it is. You also can do is like in a lot of cases, you can share the prefix. In a conversation, you can share the same prefix, or you are going to have parallel samplings to provide better outputs. And when you share the prefix, you share the sequence, like you share pages in virtual memory, right? So what is the result? You know, it's like the utilization now grows from 38% to 96%, right? So basically, now you can process more requests in parallel. You are going to have high utilization of the GPUs. Very simple idea. These are some results. It's from back then. Now, of course, many things have changed. But this was throughput, so higher is better compared with what was kind of the state of art back then, right? TGA and, you know. Now, I told you this is like virtual memory, right? So what is the kind of the differences and similarities? These are analogies. You can think about OS pages like blocks, reduce memory fragmentation, and you can also share the pages across processes. You know, like you share KV blocks across samplers, like you share pages across processes. Again, reduce memory wastage. What are the differences? Evictions. So with evictions, each page is kind of more or less independently evicted. Here, it doesn't make sense to, because you have to look at all the tokens, all the prefix to generate the next token. It doesn't make sense to evict only some tokens. Either you evict all of them or you don't evict any. So you evict at the request level. The other thing is about, as you know, in virtual memory, you save the pages on the disk and then you load them from the disk, right? But in this case, actually, in some cases, it's easier to recompute everything because due to the parallelism of the GPU, right? So there are a few things like that. So VLLM these are very old numbers. Now it's 500 contributors and probably 25K stars. But it's part of virtually every, we call these techniques, which I mentioned to you, page attention. So the techniques itself is part of VLM, of course, but it's also part of every other engine, LLM serving engine today, library. Right, and yeah, so this is basically saying everyone adopted page attention. So yeah, so that's kind of pretty much what it is, and it was. So next I have 10 more minutes for this one. So basically again, VLLM, and VLLM again is like when it's going to, you run into distributedly on multiple GPUs on multiple machine. In particular, you do tensor parallels, pipeline parallels. For that, you use Ray. Okay, any questions about this? Yes.
Yeah. So, there's been work recently on like not having KV cache and just recomputing again every time. Like, is that a viable thing for? There has been some work, like some papers recently, which is like basically not keeping the KV cache at all, or keeping very little of the KV cache and doing a lot of recompute for every token. So basically just computing the KV cache again and again for every token so that you don't have to have a lot of memory. Right? Yeah.
But it will take time, right? You can do that, but it will take time. Of course, it's easier. And then you are going also, the problem is that you're also going, another constraint is not only the memory, but it's the bandwidth, the HBM. And if you do that, you are going to consume the HBM, the bandwidth.
Right. Yeah. So I guess my question was that, does this support like, if I don't want to keep the full KV cache, but maybe keep only like the first 15 layers, the first 20 layers, something like, like, does it allow for that granularity, or is it like, because every token is actually 30 embedded, right, in the KV cache?
Yeah, I think there are many variations of that. And it also depends on the workload. This is for online. If you are going to do, for instance, offline, like batch inference, you have a lot of more degrees in which you are going to use CPU memory, and even, there are solutions now are going to use compression to actually even put some of this KV cache on the disk, and it's working quite well, right? There are many things, right? In the case of, for instance, another optimization you can make, in the case of batch inference, you can reorder the request so you can maximize prefix sharing, right? And obviously, right now, there are efforts about having, for attention, which is the attention is a very expensive, is N square. And people try now to have bigger and bigger prompts, right, and context length. So there are a lot of efforts in trying to go from N square to more linear to have. Is there a lot of, it's, but yeah, great question. Okay, so, but that's kind of what, so what is the takeaway is there? It's like, it's a pretty simple technique, which is in, in use that forever. Of course, and always when you apply the same techniques to new problems, there are also kind of variations. Like I mentioned here, the eviction is kind of different. You, instead of getting the data back, again, you can recompute it. So there are a little bit of different trade-offs, which makes the problem interesting. So this is chatbot arena. So this is again some work we started kind of around March last year. And it's about benchmarking. So large language models, how do you know how well they perform? It's a big problem. And Dave Patterson basically is what famously said, for better or worse, benchmark shape a field. And this was certainly true in AI, right? ImageNet and everything, right? Everyone knows. So, right, this is what you do. The problem, LLMs are extremely hard to evaluate, okay? And this is because expensive and it's unreliable. Let me make a point, drive home the point. Here it is. This is a prompt, right? Develop a Python program that reads all the text files under a directory and returns top 5 words with the most number of occurrences, okay? And you get these 2 answers. Which one is better? Everyone knows Python here, like it's pretty simple problem, right? Any guess? My point is take some time. Okay, that's a programming. Let's take this other one. Photosynthesis is a vital process for life on Earth. Could you outline the 2 main stages of photosynthesis, including where they take place within the chloroplast and the primary inputs and outputs of each stage? It's 101, right? It's like biology. And you get this. two answers. Which one is better, right? Not easy. So now the other problem is a data contamination. Why? Because as you know, one of the big problems this kind of frontier labs have today is that they run out of data, right? So they train on everything under the sun, including the benchmark themselves, right? So here is one example, it's like, this is core force, right? And every LLM has a cutoff date. It was trained on this data before. So this, Twitter user was observing that before the GPT was scoring 10 out of 10 on the problem which were before the cutoff date and 0 out of 10 after that. It's also this thing about, like it was this kind of another episode when it was this kind of paper. So coming up from MIT, basically saying that, hey, GPT-4 can score 100% of meet MIT EX curriculum with the right prompting. Okay. Well, it turns out that actually also the case of contamination, and this was followed a few days after, so it's only 50% or something, 58%, right? So the contamination is a big problem. You have a benchmark, large language models learn. It's like exams. You have an exam, you reveal the exam, and then you are going to, everyone will know the exam. You cannot give it again. So what is our story? This is a context, but what was our story? How we came to work on this? So in February 2023, Facebook released Llama, right? And there are Alpaca stand for doing fine-tuning on Llama. And we fine-tune this, based on Llama, Vicuña, and using the shared GPT data. If you remember, today, the shared GPT data is a kind of a service where if you have prompts from the GPT, you can share with others, right? So that was at that time, we'll took that and we fine-tune. And then the problem was how you are going to evaluate it, right? We got a bunch of students of evaluate it and things like that. But it takes long, like I mentioned to you. And so then we have the idea, it was 2 weeks after the GPT was released. Hey, we can use maybe GPT-4 to evaluate, right? How, Vicuña performs, versus Llama or other fine-tuned models, fine-tuned Llama models, like Alpaca, right? So does it work well? Well, it turns out that it works quite well. So remember, this is the first problem. The problem is the Python problem, right? So this is the answer, So the answer says, from GPT-4, when you say, you give a prompt, you are a teacher, this is a problem, exam problem, these are the results, which one is better, right? It says that, assistant A is similar, but it does not handle case sensitivity and punctuation, which B does. So B is better, right? When you look at this, it makes sense. It's easier, right? It's always, many times it's easier to evaluate the solution than come up with the solution. This is about the biology problem. And it's again, in this case, B was better because A, although it's a longer answer, it confuses the inputs and outputs from the 2 stages. Okay? Yes, all 5 minutes. So now we done that, right? But then you need somehow a ground truth, and still the humans has a ground truth, right? Again, you have students, but I want to build something more scalable. And that fundamentally, this is about how to build their ground truth, how to also have the humans provide them data from the humans, and actually our main idea, cross-check with the GPT-4, right? And you want, for every question, you want to rank all these language models. This is one way to do it, right? But of course, this is hard. If I give you to rank out, n choices, it's very hard, right? It's easier to pick the best out of n, right? And it's easier to pick the best out of 2, right? You remember this, the paradox of choice. The more choices you have, the harder it is to pick only one, let alone rank them, right? So that's basically what we said. Okay, we have to build a simple system which the user have to pick only one out of 2. And it's a little bit counterintuitive because the alignment at that time, and even today with reinforcement learning with human feedback, asks the users to rank the choices. And we have now, the next question is, how do you do it? You have 1 out of 2, but there are different ways to do it. One is tournament, right? To play each of LLM against every other one. This has a problem because it's hard to scale, and typically you need to you cannot change the composition of the players, of the team, how many teams you have and which teams you are going to play over time when you do this. But fortunately, there are all these other kind of rating systems which basically it's used in tennis, ATP, in soccer, cricket, whatever, right? And of course, also it's in chess. Right, so we kind of started with kind of ELO rating, which allows you to come up with an absolute ranking, even though 2 players may never play between them, right? So this is our chatbot arena. You go there, you can ask your questions, you get to answers, and you can say A is better, B is better, or tie, and so forth. Or none of them is good. And we take that into account, and we come with these scores. This is the score arena scores, which is basically a sophisticated, a better ELO. And this is what is today, it's from yesterday, I believe, right? And this we rank all these models, right? It was much more successful than we expected. Also, in retrospect, one of the things it gives you also, it makes free to try all these models. So, free is good, right? It's like, so we accumulated over 60 million charts and over 2 million votes, right? You see there a spike. This is the number of charts per day. A spike, do you know what the spike was? When it was rumored that OpenAI is going to test GPT-4 or before being released, a lot of people try to come and to see how it's working, to try to identify which one it is. It was anonymized, but still. And this is a distribution about on languages of the votes, and this is log scale, right? So obviously, most of them are United States and China, Russia. Yes, I know. So the next question, okay, so now we have this data from the users. We have the GPT-4 as a judge, GPT as a judge. How reliable it's to use this LLM as a judge? And we made these studies, and surprisingly or unsurprisingly, they are more or less like humans. They exhibit biases. Position bias, they prefer the first answers. Verbosity bias, prefer the long answers, the more verbose answers. Self-enhanced bias, they prefer answer from themselves, obviously. And limited reasoning, they are not as good as grading math questions. They are not as good at back then, right? And you can account for these biases, you can reduce them and so forth, or factor them out. But the other problem is that the agreement, right? The other important data, right? Because 2 humans are not going to agree 100%. So now what is the agreement between 2 humans and a human and large language model? The TLDR pretty much the same, right? Between humans and LLM, 85%, between 2 humans, 81%. So LLM as a judge works quite well. Status, this is next to last. I have only one. So it was an effort. We didn't know what to expect when we started. Again, we started this for us to try to evaluate our own models. But right now, it's quite successful because, not because it's maybe the greatest things to evaluate large language models, but the other methods are pretty bad. So you are, and now many of the frontier labs, they evaluate the model on Chatbot Arena before releasing it. We release 20% of the votes on periodic basis. We don't release more because we try to avoid a little bit of contamination, although we do get fresh votes all the time. We have an Arena hard data set because people ask, give me, the harder questions. And one way we do, there are a few ways to do that, but one way to think about what we do is our questions for which the best models and the weaker models give different answers. And we have new evaluation, image evaluation, and soon we are going to have more evaluation built on top. So in summary, I think, like open source, I am, very bullish on open source. We believe it's future of AI, at least as a stack. And we presented 3 projects: the Ray to scale and productize various AI workloads, VLLM, which is a high throughput LLM inference engine, and Chatbot Arena, it's a system to evaluate large language model. And again, we are just scratching the surface. A lot of more things to be done here. Thank you, and sorry for taking so long. I'll be around, so you can, since we are running.
Thank you so much.
Okay.